Okay, this talk is actually a follow-up on the previous talk. Okay, so the work I'm going to present is, to a large extent, inspired by Professor Singh and his collaborators did. It's from space-time singularities. Let me start from the beginning. So we know that, according to the classical theory described by Einstein's field equations, space-times must generically develop singularities, Big Bang or Big Crunch. And usually that's taken as a signal that the theory breaks down there. And the hope is that some future theory for gravity will solve that problem, will eliminate the singularities. In particular, we have some indications that we need to go with a quantum theory for gravity. Okay? And maybe a quantum theory for gravity will eliminate those. Well, we don't know what the quantum theory for gravity is. And last time I checked on Wikipedia, there was like 22 approaches mentioned. So you might imagine that the answer will depend on which approach to quantum gravity you take. You've seen that in the previous talk. Indeed, if you take loop quantum gravity or Witt quantization, you seem to be getting different results. What I'm going to illustrate in this talk is it might also actually depend on which approach to quantum mechanics itself you take. Okay? Whether you take a Copenhagen interpretation or a collapse theory or consistent histories or a Bohemian formulation. So this is a summary of the results that the previous speaker mentioned. So I'm not going to discuss all these 22 approaches to quantum gravity. I'm just also going to restrict myself to really the Witt quantization and loop quantization. And so in the context of standard quantum mechanics, Prof. Singh and his collaborators showed that for really the Witt quantization, you have singularities for a certain class of wave functions, whereas in loop quantum gravity, you don't have singularities. Of course, you use Copenhagen version of quantum theory, so in analyzing these questions, there's some hand-waving involved. So you have to go beyond standard quantum mechanics to make a precise analysis of these things. So one way to do that is using consistent histories. And there, as was explained in the last lecture, for really the Witt quantization, you always have singularities, while as for loop quantum gravity, you have no singularities. What I'm going to illustrate in this talk is that if you take the Bohmian point of view, if you take the Bohmian approach to quantum mechanics, really the Witt quantization, there may or may not be singularities. It's going to depend on the wave function and the initial condition. And if you go to loop quantum gravity, I can show that there's no singularities, okay? Whatever the wave function is. Here is an outline. So first I'm going to say some words about Bohmian mechanics. Then I'm going to say how that deals with quantum gravity, and then I'm going to go to singularities. So the non-relativistic theory, non-relativistic Bohmian mechanics, what is it about? Well, it's about point particles moving in space. So in a non-relativistic description of the world, stuff is made out of point particles, tables, chairs, it's all made out of point particles. And the way they move is, through this equation. So it's a first order differential equation. It says that the velocity of the particles is given by this function of the wave function. Okay? So you can express it as the gradient of the phase. The wave function satisfies the usual Schrödinger equation. So this theory solves the measurement problem. There is never any collapse of the wave function, so you don't have to refer to measurements as something special. And for example, like Schrödinger's a cat, whether the cat is alive or dead depends just on where the particles are. Okay? Either they make up a live cat or they make up a dead cat. These are trajectories for the double slit experiment. If you would do this experiment one electron at a time, one of these trajectories is going to be realized. You see that the trajectories tend to bunch up where you have a constructive interference, and tend to avoid regions where there's destructive interference. So There's also a deterministic theory, so how do probabilities come out? Well, that's some ignorance over initial conditions. If you have an ensemble of systems all with the same wave function, like in the case of the double slit experiment, even though the wave function is the same in each time, the initial position can be different each time you do the experiment. That's going to lead to a different result at the final detection. And there's a special distribution, and it's the modulus of psi squared, okay? That's the usual position distribution in quantum mechanics. In the Bohemian theory, it plays the role of an equilibrium distribution. And it's a special distribution in the sense that, well, if you had a distribution at one time, you had a distribution at all times. So the Bohemian dynamics preserves this distribution. That's crucial if you want to show how standard quantum mechanics follows from Bohemian mechanics. So from the point of view of Bohemian mechanics, standard quantum mechanics comes out, okay, using this property and a little work. Standard quantum mechanics falls out as an effective theory describing the physics of equilibrium. There's a lot of things you can do with this. For example, you can study the classical limit. So when do you have the classical limit? Well, whenever these trajectories are approximately classical, okay? Whenever they satisfy the classical equation, in this case, Newton's equation. That's how you get out the classical limit. Another thing is that there's a nice way to define the wave function of a subsystem. So if you consider a Bohemian description of the whole universe, we'd have a wave function of the universe, and then a certain number of particles in that universe. What is the wave function now of, say, a single particle? Well, this is the way how you define it. I suppose you just have two particles. Okay, so you have a wave function, and you have two positions, as functions of time. And you can define the wave function of system 1 as follows. So chi is the wave function of system 1. You define it in terms of the wave function of the universe, total wave function, and the position of particle 2. So you just plug it in, the position of particle 2, here. So this wave function gets an extra time dependence, so there's the explicit time dependence here, and there's also the time dependence because this second particle moves in time. So if you would calculate the time derivative of this wave function, you may or may not get something like Schrödinger equation, the effective Schrödinger equation. It's going to depend on the system. And it's a natural definition for the wave function of a subsystem. Why? Well, if you calculate the velocity using the wave function of the subsystem, or you use the total wave function, you get the same trajectory. So it doesn't matter for the trajectory if you calculate it using the wave function of the subsystem or the wave function the universe. And this wave function is actually also the wave function that would collapse in measurement situations. You can easily show that, a simple exercise to show that this wave function of the subsystem, if you perform a measurement, this will actually collapse, just the way it happens in quantum mechanics. So this is how we can explain the success of the collapse rule in standard quantum mechanics from Bohemian. So now to quantum gravity. Well, this is really the Witt quantization. Well, we've seen it already a couple of times. So how does it arise? Well, you just use the canonical quantization procedure that was very successful in high energy physics. So you just apply it to general relativity and see what comes out. If you do that, well, the basic variable that's going to be quantized is a spatial metric, so a 3 metric in spatial hypersurfaces. And your quantum states, that results from the quantization, is going to be some quantum states, so some functional of this 3 metric, and the other degrees of freedom, the matter degrees of freedom. For example, a scalar field. And this satisfies a certain wave equation called the Wheeler-DeWitt equation. So this form, one particular feature is that the Hamiltonian acting on the wave function is 0. This in particular implies that the wave function doesn't evolve in time. So there are some technical problems with this theory. There's also some conceptual problems. The measurement problem again. Okay, and this was emphasized already a couple of times. If you want to apply the theory to the whole universe, or if you want to describe the early universe, this is getting way more serious than in non-relativistic or in ordinary situations. And secondly, there's also the problem of time. Okay? So this equation tells you that the wave function doesn't evolve in time. So how can we explain from this theory that the universe seems to be expanding? Now, in a Bohmian approach, what you do is you postulate that that the wave function is not a complete description, but there's also an actual metric. And the way the metric evolves depends on the wave function. And even though the wave function might be static, in general it will generate non-trivial dynamics for the metric. So again, this theory doesn't solves the measurement problem. And now we can tell whether the universe is expanding or not. We just have to look at what this metric is doing. Okay? We just have to calculate it. And something else, so we can also derive like time-dependent Schrödinger's equation from this formalism. Just using what I just told you about this wave function of the subsystem. So if I do, for example, if I have, so suppose I solve these equations of motion here, I get an evolution for the actual metric, for the Bohmian metric, the Bohmian matter fields. I can use this time evolution of the actual metric, plug it in the wave function of the universe, this static wave function. So the wave function for the scalar field then will depend on time through this metric. So then you can analyze what kind of equation, what kind of effective equations this is going to satisfy. And of course, what this guy is doing. Coincidentally, something like this has been proposed also by Banks. But in Banks' situation is pretty ad hoc. He just says, okay, why not put in a classical solution here for the metric? So he gets his time dependence just from putting in a classical solution. And then for him, it's kind of ad hoc. So I've shown you why this is a reasonable definition in the context of the Bohmian theory. Before I go to singularities, let me also make some publicity for other work I've did using this framework. One of it is in these cosmological, in the context of cosmological fluctuations. We've heard a couple of talks on this. One was just a couple of hours ago. So there's two problems with vacuum fluctuations in cosmology. Okay? One is in the early universe, and one is in the late universe. Both eras, you have an exponential expansion of the universe. The early universe is driven by inflation. In the final universe, it's driven by the cosmological constant. And you have worries in each era. So in the early universe, you have this problem of the seeds of structure. So you start from the vacuum state, which is homogeneous and isotropic, and you want to get out classical fluctuations, which are not homogeneous and isotropic. How do you do that? Okay. So within the Bohmian context, well, the wave function might indeed be homogeneous and isotropic, but there's more than the wave function. There's also an actual inflaton field. There's also an actual metric. Okay? And the perturbations of this actual metric and inflaton field, these are not going to be homogeneous. Okay. So in this way, you can explain the classicality and the inhomogeneity of these inflaton fluctuation. And the second problem is, that's a worry that some cosmologists seem to have, is about Boltzmann brains. So in the late universe, there's an exponential expansion of the universe driven by the cosmological constant. So all matter will be dispersed away, so there will be nothing left, basically. It's just going to be vacuum fluctuations. And the idea is that from the vacuum, all kinds of fluctuations might happen. All kinds of stuff might appear in that vacuum, like tables, chairs, spontaneously being created. In particular, also brains, okay? Disembodied brains, or maybe even with a body to it. And that leads to some kind of problem. Me, myself, I'm not convinced really that it's a problem, but suppose you think that's a problem. Well, if you analyze this from the Bohmian point of view, well, what does the Bohmian theory tell you about these fluctuations? Is really stuff popping up? Well, then the answer is no. If you have the vacuum state, the Bohmian dynamics is really boring. So what it's going to do is there's going to be some fields in space, but it's not going to evolve. Or, well, it's going to evolve, but it's just going to follow the expansion of the universe. So this field is going to be static, but it's just going to be stretched by the expansion of the universe. So the Bohmian field is not going to fluctuate at all. Okay. If you're worried about this from a Bohmian point of view, there is no worry. Another thing is semi-classical gravity. We've also already seen that. So how do you couple classical gravity to quantum matter? One way to do that is, like in Professor Sudarsky's talk, is take an expectation value for the quantum matter and let that energy momentum tensor be the source in the classical Einstein field equations. Now, using the Bohmian theory, there's another approach you can take. Instead of coupling that to the expectation value, you can choose the actual energy momentum tensor of the Bohmian scalar field. So if you describe quantum matter, there's going to be an actual Bohmian scalar field. It's going to define an energy momentum tensor. Why not plug that in? Depends on which T you take. Okay. If you do the naive thing, it's not going to be conserved. So you have to do some work to do this. That's what I've done in this paper. So quantum chemists have actually done something similar, not in quantum gravity, but for non-relativistic quantum systems, like having a coupling between quantum systems and classical systems based on Bohmian ideas, okay? And they found that these Bohmian formulations always gave you better results than the usual mean field approximation, or the same results, okay? So even if you don't like the Bohmian theory, here you have like a practical application of it. So here you can put it to use as semi-classical approximations to the full quantum. Okay. So the hope is with this program, maybe, because nobody knows what the quantum theory for gravity is, maybe using these semi-classical techniques, maybe you can already probe a bit into the quantum gravity domain. Now, singularities. So with the problem of singularities, well, the problem that poses itself within the standard quantum context is that, well, of course we have this problem of time and all that. There's an extra complication now if you want to talk about singularities. The question is actually, what do you mean by a singularity? And in the literature, different definitions have been proposed. Like that the wave function has support on singular metrics. In the Witt, no, I'm sure the Witt took that as a definition of singularities. The wave should avoid singularities by having wave functions that have no support on singular metrics. Other definitions you can find is that the wave function is peaked around singular metrics, or basically that the expectation value is singular. But none of these is really satisfactory. In some cases, they can give you some clues of something, but in general, these are not very satisfactory. For example, the last one. So the expectation value is non-singular, so the expectation value over an ensemble of universes is non-singular. What does it mean for our single universe? So in the Bohmian program, this is, the question is simple, it's just the same as in the classical theory. You have singularities whenever the metric is singular, whenever this Bohmian metric is singular. The question is easy, now we just have to answer it, see what happens. So I'm going to consider the same framework as Param Singh, just in the other lecture. So just simplified models, Friedman-Lemaitre-Robertson-Walker spacetimes. So you have a homogeneous isotopic space, and it's described by this metric, and there's a homogeneous matter field. In the previous talk, there was also a lapse function here, n. Okay. This just makes it explicit that the theory is parameterization invariant. I just always take n equal to 1, just for notational convenience. In all the Bohemian approaches I'm going to describe for relativity theory and loop-on gravity, it's actually time reprimatization invariant. So I could have kept this n everywhere. Okay. It just doesn't matter. So the time I'm using here is the time for an observer moving with the expansion of the universe. So classically, you've seen this before. Classically, you always have singularities. So, sorry, let me say this again. So classically, you have these equations. There's one particular solution which gives you just a static universe, so where the scale factor is constant. So, of course, in this special case, there's no singularities, but otherwise, you always start from a Big Bang or a Big Crunch. So the scale factor either goes like that over time, or you have the time reversed. The scale factor just goes to 0. And I'm going to also use this change of notation too. I'm going to use alpha, which is the logarithm of the scale factor, because alpha is unbounded. And singularity means that A is 0. That means that alpha goes to minus infinity. I'm going to often use plots in phi alpha space. So these classical trajectories here, these correspond to these classical trajectories. So a trajectory like this, so remind alpha going to minus infinity is the singularity. So these trajectories, they start from here. So this is a Big Bang. And then you keep expanding. If you go in the other way, that's a Big Crunch. Similarly for here you start from a Big Bang, keep expanding, or you go the other way, time reversed. Keep contracting until you hit the singularity. You have a Big Crunch. Now the Wheeler-DeWitt theory, that's what you end up with. It's easy to solve. Well, you just have the solution of just the traveling waves, so the solution's just the right moving and the left moving wave function. So either it's the difference between alpha and phi, or depends on the sum of alpha and phi. And you can picture that as psi r. You translate that as in this direction. Or psi l, you translate that in that direction. So you have, the wave function is like this. Okay. Of course, phi is not time here, just to illustrate what wave functions look like. Four-dimensional, yeah. So that's going to be, it's not clear from this equation, right? But in the Bohemian theory, well, I'm going to introduce again this metric, okay? Four-dimensional space-time metric. There's going to be an actual scale factor now. The way the scale factor is evolving in time is now not determined by the classical equation, but by the Bohemian equation. And these are here. The way the scale factor, or alpha, evolves in time is determined by the wave function. Now we can look at solutions for the wave equation and see what the Bohemian trajectories are doing, whether we have a similarity or not. One simple solution that you can immediately see is that, well, if the wave function is real, okay, then the solution is static. So alpha is unconstant and phi is constant. So that's Minkowski space now. In this case, you have no singularities. It doesn't correspond to what we see, so the universe is not static, so this is empirically ruled out. Can you have other solutions? Well, there's a whole class of wave function that doesn't give singularities. Okay? If you assume this, that is psi r and psi l's, that they go to 0, that they're 0 for x going to minus infinity, then you can show that the only solutions that never give a singularity, so whatever the initial conditions for the Bohemian fields are, you never get a singularity. Well, these are of this form. Just the real part of the psi r, the real part of, it's the amplitude of psi r, the amplitude of psi l, and then some phase factor here. Wave functions of that form never give singularities. Whatever the initial Bohemian conditions are, you never get a singularity. For example, if you use this special choice, okay, then you can integrate that and you can show that all the paths in alpha phi space are circles. What it means is that, well, you have a cyclic universe. Yeah, exactly. So in the previous talk, it was concluded that you always have singularities within the Broglie-Bohm theory. Here you see it's not the case. Okay, even you can impose that, right? And I think you do impose that. So, but then your wave functions are not normalizable, expected that measure usually is. But if I impose this condition, these are still allowable solutions in your case, right? So even for these wave functions, you conclude that there's no, that there's always a singularity. So let me come back to the difference. So we get different answers just because we are using different approaches to quantum theory. Okay? Consistence in histories and Bohm mechanics might tell you different stories about histories of the universe. This was already something noted before. Yeah, you're not going to see the difference in the lab. That's right. Sorry? Yeah, but let me come back to this. So these wave functions don't give singularities, but then, well, all the others give at least a possibility of singularities. For example, if you just have a right-moving packet, well, nothing is moving here, but if you have this psi r, then you have these trajectories, so you have the classical trajectories, and you always have a big bang. Or if you have psi left of this form, you always have a big crunch. That's for any wave function psi r, basically, you get the same story. If you either have psi r or psi left, and there's no superposition, then you have this story. If you have a superposition like this, so that's just a superposition of the two previous wave functions, you have a different situation. Then here you have recollapsing universes. Okay? And here you have bouncing universes. Like here you could say like half of the trajectories are non-singular. Half of the possible universes give you a bounce. It depends on your initial conditions. So some remarks. So in the Bohmian approach, so we have an external time t. Okay. Of course, this time t, you can always rescale time, so this shouldn't lead to physical differences. Of course, we should express the gauge invariant content in terms of physical clocks, right? Build up from matter fields. We can do that in this case, for example, if this phi, the scalar field, this Bohmian scalar field is monotonic in time, but then you can use it as a clock. Okay. For example, you can then express the scale factor as a function of this physical clock phi. Another thing is, well, Prof. Singh talked a lot about probabilities. Well, here if I want to talk about probabilities, I will have to do some work first. Because this wave function psi, well, naively you might think, okay, this gives you probability density, alpha and phi, but this is not normalizable. Still, you can use this quantity to extract some probabilistic statements, but it requires some work. What we did in another paper to like really compare to what was done in the loop quantum gravity community, in particular with these consistent histories, was as like a toy model. We also used phi as an actual time. Suppose we also interpret phi as a time. We have these wave equations, and then we construct a Bohmian dynamics, which is different from the previous one, where phi is really treated as time from the start. And then you can talk about probabilities again, because you introduce the dynamics which conserve the usual psi squared distribution, the same distribution that was mentioned in the talk before. And then you find, then you have the following situation. There's 4 types of trajectories you can have. you can have the classical trajectories, like those starting with a Big Bang or ending up with a big crunch. There's also the recollapsing universes, and there's the bounces possible. So all these things are possible. And for a certain wave function, this is what can happen. So these trajectories here, these are recollapsing universes. These start with a Big Bang and keep expanding forever. And these are the bouncing universes. And for any wave function, you can show that the yeah. Time reverse to. So in each case, whatever the wave function is, in this case, if you treat this phi explicitly as time and you use the math using phi as time, find that probability of a singularity is at least 1/2. There's a possibility, non-zero probability of having a bounce, okay? It's always going to be smaller than 1/2. In the best case, there's 1/2 probability for having a bounce. And so coming back to the difference between consistent histories and the Bohemian case, there's already a paper by Hartl comparing these two, and it's basically the same situation that happens here. So he considered a packet, superposition of packets. So your wave function is a superposition of psi1 and psi2. And this packet moves like this, and this packet moves like this. And he analyzed that the coarse-grained histories that decohere are inconsistent histories about it's either like this. These are the coarse-grained histories. This one going like that, or going like that. But in the Bohemian case, the Bohemian trajectories are not like that. So the Bohemian trajectories can actually not cross. If these were two possible Bohemian trajectories, they would cross here. And that would mean that you have two solutions with the same initial position. But remember, the Bohemian dynamics is first order, so given an initial position, you have a unique trajectory. So this can't happen. So purely from geometrical reasons, something like this must happen. That's also what you see in the graph. Trajectories don't cross here. Whether this is an artifact of the simplified model or not, I suspect something like that is also going to hold in more general cases. Okay? In full quantum gravity, there might be trajectories which are non-singular, and trajectories will be singular. So now, loop quantum gravity. I'm glad there was already an introduction to the wave equation here, so I can just copy this from the previous talk. So what we have here now is the following wave equation. So instead of here before in the related width theory, there was a minus d alpha squared. This now becomes a difference operator. So this operator acting at psi at nu that is proportional to a cubed, so the scale factor cubed. This operator acting on psi at nu gives you some superposition of psi at nu plus 4 lambda, psi at nu, and psi at nu minus 4 lambda. So there's certain discreteness entering. You can do a Bohmian formulation of that. What's going to happen in this formulation is that the scale factor again evolves continuously. There's again, the scalar field is going to move continuously. There's also going to be a scale factor, but that scale factor is not going to evolve continuously. It's going to jump. It's going to jump between these discrete values. A or a to the 3 is going to jump plus 4 lambda or minus 4 lambda. So this technique of having like a jump process, a Bohmian jump process that was first introduced by John Bell. He constructed some Bohmian theory for lattice quantum field theory. And in that lattice quantum field theory, his Bohmian ontology was like the number of fermions at each lattice point. And the dynamics was just that you had the dynamics was such that you had a Markov jump process, so at random times, these fermion numbers could change over time. So the math that goes into this, constructing this, is exactly the same. So phi dot is given by this expression, so it evolves continuously. The scale factor, or a to the power 3, that doesn't matter. There's some certain jump rates for it. So to jump from nu to nu plus 4 lambda, or, this is to jump from nu plus 4 lambda to nu. And these are the jump rates to jump from nu to nu plus 4 lambda. What do you mean? I postulate the stochasticity. So these are jump rates, the probabilities of per unit time to jump. Yeah. That's the theory. That's the dynamics of the theory. Differential equation for phi, jump rates for the scale factor. This is probability per unit time to jump from nu plus 4 lambda to nu. So at random times, so the scale factor has a certain value, and at random times, a certain exponential distribution, you get a jump to a higher scale factor or a smaller scale factor by a certain constant. And then you can just add, so what does it mean to have a singularity? Well, either, let me go to the next slide. So if you know that the singularity, then you can calculate probability to actually jump to the singularity. These jump rates give you transition rates, jump into the singularity. So, and you can only go to the singularity by going to by passing through the nearest neighbor. You have a kind of lattice structure for the scale factor. Okay? 0, and then there's a certain value here. And the value of A is hopping around between these values, and then it hops here. What's the probability to jump to 0? So what's the probability to evolve into a singularity? Well, the transition rate, if you calculate it, is just 0. And likewise, if you would start here, there's 0 probability to jump to epsilon. So that means that you will never end up in a singularity, or you will never, if you start in a singularity, you never get out. So you can just ignore these questions. Yeah. Given the wave function, there will only be a probability to jump forward or to jump back. No. Indeed. Yeah, so that's what I'm saying. Yeah. Exactly. So this is the conclusion. So at least in this simplified model, you may or may not have singularities in the relativity theory. In loop quantum gravity, you don't have singularities. And the basic reasons why you don't have singularities in loop quantum gravity, well, they're going to also be valid in other situations, I believe. If the probability density is 0 here, then by construction of this jump process, you will never jump into the singularity. Just because of the obstruction. So the heuristics is that the Bohemian configuration can jump here, but never can go there. Like in the continuous case, the Bohemian configuration, there's nothing that obstructs it to go to 0. The probability density is 0 there. As you've seen, in many cases, it will go to 0. So another thing is, the property of this jump process in loop quantum gravity, if you take the continuum limit for non-zero scale factors, you get exactly the Wheeler-DeWitt theory, and you get the Bohmian version of the Wheeler-DeWitt theory. The continuum limit for positive large enough scale factors, you get back the Wheeler-DeWitt theory and the Bohmian evolution. Good. So these were the results for simplified theories. Of course, it's the question what happens in more general theories. Okay. More general approach to quantum gravity. That remains to be studied. Thank you.
So I think it will be a very useful exercise if we can also compute observables in this approach. Because like, though we have this nice geometrical picture when the singularities can occur or not occur, I think it's very important that we also understand like what happens to observables. Like your interpretation right now is without these observables. Right? I think you can easily define that, these Dirac observables.
Yeah. Well, but here in this case, what is observable is, well, just the graph in alpha phi space that contains all the observable constants.
I think it is very important because like we have to make sure that this observable commutes with the Hamiltonian.
But here it's in a different